Let's just wait for some more time and then we'll begin. Just a couple of more minutes. So let's begin. Hello everyone, I'm Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. So today we'll discuss the questions of week 3 assignment and we'll go over some of the questions to solve week 4 assignment. Okay, so let's begin. Yeah, so this was the data given for the first set of questions in week 3. Let's just go through the data given to us. So consider the following aircraft. Am I audible? Can you just confirm? Just put it up on the chat box or something. Am I audible? Thank you. Okay, so the data given to us is the weight of the aircraft, the cruising velocity, the area, the density at the cruise altitude, the aspect ratio, XCG and XAC, which are the same thing in this case, the neutral point. Then they've given you some aerodynamic parameters of the wing and the tail, the CMAC of the wing, CL alpha of wing and tail are the same. The angle of attack at zero lift, the wing and tail setting angles, the tail efficiency factor, VH is the horizontal tail volume ratio, the epsilon E of the Oswald's efficiency factor, tau is the control surface effectiveness parameter, delta E max, maximum deflection of the elevator, and they've given you some formulae, so which makes solving the questions fairly simple. Okay, let's just go over it. And before we proceed, this formula, remember that it gives you the angle in radians, right? So it gives you in radians. Similarly, its rate, d epsilon by d alpha, all of the parameters on the RHS of the equation should be in per radians or radians. Okay, then only the equation is valid. All right, so let's proceed. The first question is very simple. They've asked you the lift coefficient for cruise. Cruise is what? When lift is equal to weight. So lift is equal to weight for cruise. Then they've asked you to find out the coefficient of lift. You know the lift formula, directly substituted, you will get the coefficient of lift. So this is the formula for lift. And then you need CL. CL is 2L by rho v square S. And for cruise lift equal to weight, so this is nothing but 2W by rho v square S. That is 2 into 240 into 9.81. Density at the cruise altitude is 0.79. 0.79. Velocity is 118 square. And you have the area as 57.5. So let's just calculate this quickly. 2 into so I'm getting the, just correct me if I'm wrong at any point. So I'm getting something around 0.7631. So it's the fourth option. All right. So let's go to the next question. Next question was calculate the downwash angle at tail in degrees. Okay. Downwash angle at tail. The formula is when they've given you alpha at zero lift. This is alpha at zero lift, which is equal to minus 2.2 degrees. Okay, I think they're missing a degree there, but let's just presume it's degrees and proceed with that. Okay, so CL naught would be what is the slope? Okay. That is given in per radians, and your angle of attack is in degrees. Okay, so 4.634 per radian. You have to convert the per radian to per degree. So that will be 57.3 into 2.2. So this will give you, let me just calculate this. So it gives you 0.1779. Okay, so that gives you CL naught. So if CL naught, like in our case, CL naught is 0.1779, what type of airfoil is it? What type of airfoil will it be? Just take, we've done this in the first few, I think both of the first lectures. If CL naught is positive, what kind of airfoil will it be? And all of you knew this even the last time. So CL naught is positive, what kind of airfoil is it? Symmetric, cambered, reflex, what is it? It's a cambered airfoil, right? That's why you have lift even at 0 degrees. Okay, so it's a cambered airfoil. Cambered, okay. We have positive CL naught. If it was symmetric, it would pass through the origin and your CL naught would be 0. Okay, okay. So now let's go ahead with finding epsilon naught now that you know CL naught. So epsilon naught is 2 into 0.1779 by pi. E is 1. Aspect ratio is, what is the aspect ratio? The aspect ratio was given, right? I remember reading it. Yes, 5.3. 5.3. So let's just calculate this value quickly. Yes, 5.3. So the value you get here will be in radians. Okay, so I'm getting around 0.0214 radians. To convert it to degrees, multiply it by 57.3. Okay, so just multiply it by 57.3. What do you get? You get 1.2246 degrees. This is your answer. 1.22 degrees. Again, correct me if I'm wrong somewhere. Okay, so this is it. Next question was CM0 contribution of tail. This we had done in the previous assignment also. So it's again very simple. The formula is already given to you. Just plug in the values and you should be able to get it. So let's just do that. VH is, where is VH? Yeah, 0.48. Efficiency factor is 0.85. CL alpha tail is same as CL alpha wing, which is 4.634. But since all of our angles are in degrees, we convert this per radian to per degrees. Anything, okay, just make sure that both the units match. Either convert degree to radian or convert the per radian to per degree, okay? So for both of these cases, what we do, divide by 57.3. I wing is 3.3. Epsilon naught, we just calculated, is 1.22. And I tail is minus 2.6. Now, what is the answer of this? Six. So it comes to 0.2349, approximately 0.235. Okay, so this is the answer that I'm getting. Okay, let's go to the next question. What is the overall CM0 value of the aircraft? Any ideas as to how to proceed with this? We have found out the CM0 contribution of the tail. What else is left? Again, this is given in the formula. So CM0 of wing plus fuselage plus tail. And in the question, they've told you that the fuselage contribution is 0. So it's just wing and tail. So now that we've found out tail, what is left? Only wing. Any idea what the formula would be? CM0 contribution of the wing. It's one of the first equations that we had derived. We had derived it even in the tutorial session actually. So CM0 of the wing has two contributions. That is, one is from the CMAC wing. What is CMAC wing? When we transfer the forces, aerodynamic forces from the CP, center of pressure, to the aerodynamic center, it comes with a moment. So if CMAC is positive, in this case, okay, it's negative. Your CMAC, sorry. Here your CMAC is minus 0.13. What kind of airfoil is it? If it's 0, what kind of airfoil is it? If it's negative, what kind of airfoil is it? If it's positive, what kind of airfoil is it? I'll repeat again, CMACW, this factor comes into play because we transfer the aerodynamic forces from the center of pressure to the aerodynamic center. Okay, so you have your, if this was your airfoil, this is your AC, this is your CP, this is where your lift and drag actually act. Now, when I bring it to the aerodynamic center, it comes with a moment. Okay. Now, in our case here, you can see that the value is minus 0.13. So what kind of airfoil is it? What kind of airfoil is it? For negative CMAC, what kind of airfoil will it be? Is it symmetric, cambered, reflex, or anything? Just try. For a negative CMAC at the wing, what kind of airfoil would it be? Just a guess. Symmetric. Okay. Why do you think for negative it is symmetric? Just try to reason it. We'll just discuss it out. Okay. If it's symmetric, why did you come up with that idea? Just a guess. Okay. So for a cambered airfoil, your AC is ahead of the CP like I've drawn in the figure here. Okay. So when I transfer these lift and drag to the AC, pitch down or pitch up moment comes at the AC. The figure that I've drawn, the exact figure that I've drawn, when I transfer the lift and drag from CP to AC, there is a moment. Is that moment pitch up or pitch down? The one that I've drawn in the figure. Pitch up or pitch down? Nose up, nose down. What is it? Or clockwise, anti-clockwise? What is it? The moment that I've drawn in the figure is the moment. So is that clockwise or anti-clockwise? Anti-clockwise. So anti-clockwise in our case, is it pitch up or pitch down? Pitch down. And our convention was pitch down is negative, correct? Yes. So Sandra, you're right. It is down, pitch down. Pitch down is negative. So in this case, in the case of a cambered airfoil, the moment that comes when you transfer the forces from CP to AC is negative. So in this case, your CMAC is negative. Okay, so it is a cambered airfoil. Now, if it was symmetric, what would the difference be? CMAC will be a 0 or positive, or will it still be negative? For cambered, it is negative. If it was symmetric, what changes would come, or would there be no change? CMAC of a symmetric airfoil would be 0, positive, negative. What would it be? Zero. Correct, Sandra. You're right. Why is it 0? It's 0 because for a symmetric airfoil, the aerodynamic center and the center of pressure are the same. All right. So when you transfer the forces, your lift and drag will not contribute to any moment, right? It's at the same point. So CMAC equal to 0 is for symmetric. Now, if your CMAC is greater than 0, what kind of airfoil is it? Reflex airfoil, exactly. What was the difference with the reflex airfoil? There was a slight curvature at the, it's a cambered airfoil, but there is an upward camber towards the tail, which is what makes your CP ahead of the AC, and you have a positive CMAC, positive moment, pitch up moment. Okay. So just remember this: pitch down, anti-clockwise, that is pitch down, nose down is negative by sign convention. Nose up is positive by sign convention. Okay. All right. So in our case, now it is negative, so it is a cambered airfoil. Another one reason how you know it is a cambered airfoil is the this value. What this means is that your CL0 is positive. CL0 is positive only for a cambered airfoil. For a symmetric airfoil, your CL0 will be 0. So the curve will pass this curve. This curve will pass through the origin. Alright? Okay. Where were we? Okay. So now let's just substitute these values and find out the CM0 contribution of the wing. It has two contributors. One is CMAC wing, that is from the airfoil characteristics itself. And this is from your CG and AC location. Okay. So let's try to calculate this. CM0 W, CMAC wing is minus 0.13 plus CL0. How much is CL0? We just calculated it. 0.1779. 0.779. And your XCG minus XAC. Now in this question, your XCG and XAC are the same, right? So it's given as the same quantity. So this will be 0. So CM0 of wing is just minus 0.13. Now the overall CM0 is CM0 wing plus CM0 tail plus CM0 fuselage. This is 0. Okay, CM0 wing is minus 0.13. Tail was 0.235. So the final answer is 0.105. Okay. Now your CM0 is positive for this entire aircraft. What does it mean? What is the physical significance? What does it mean? Do we want it to be positive? Do we want it to be negative for a typical aircraft? CM0, the CM0 value, do we want it to be positive or negative or 0? What do we need it? What do we need it to be? For a typical aircraft, what do we need CM0 to be? Positive, negative, 0? Again, guess. Let's start with your guesses, and we'll try justifying or whatever. At least guess. Positive, yes. So we had studied two conditions initially. One is that CM alpha should be negative, and I had repeatedly said that CM alpha negative is the only condition for static stability. The next condition that we studied was CM0 should be positive. It does not affect stability in any way, but CM0 should be positive. Why? We want it to be positive. Can you try and let me just draw the graph? So this is your CM versus alpha graph. For a stable aircraft, you need CM, the slope should be negative. And now, like Sandra said, the CM0 has to be positive. So your slope will be your graph will be something like this. And this is your CM0. Now, if it was CM0 was negative, okay? So this is A and this is B. Can you tell me why, by looking at these two graphs, can you tell me why we prefer CM0 to be positive? Again, it's not a mandatory condition, it's just a preference. We prefer our aircraft to have positive CM0. Just look at these two graphs and try to tell me why. We can't trim when it's negative. Exactly. To trim your aircraft at a positive angle of attack, we require CM0 to be positive. Now, if this were the case, if your CM0 was negative, your trim happens at negative angle of attack, which is not desirable. If CM0 is positive, trim happens at positive angle of attack, which is what we want. Okay. So that is why CM0 is positive. Okay. So for this aircraft, it is true. CM0 is positive. You can trim at positive angles of attack. Okay. Next question. What is CM delta E? It's a direct substitution of formula. Let's just put in the values. Minus 0.85. VH is 0.48. CL alpha tail is 4.634. They've asked you in per radian, so there's no need to convert it. And your tau is tail efficiency, control surface effectiveness parameter, which is 0.46. So how much is this value? So I'm getting it around -0.8697 per radian. This is the one. Okay. Now this is negative. Can you tell me why we need it to be negative? Not why we need it to be negative. Why is it negative? Cm delta E. What is Cm delta E? Is dCm by d delta E. Change in the pitching moment due to elevator deflection. Why is it negative? Just try and tell me why is it negative? Let's just take a simple case. If I deflect the elevator, okay, before that, conventions. If I deflect the elevator down, is it positive or negative? Elevator deflection down, positive or negative? Elevator deflection down is positive. Okay. So when I deflect the elevator down, it changes the camber of the airfoil. What happens then? That lift is increased. Okay. So just try to remember it that way. Since you have a positive lift generation when you deflect the elevator down, it is considered positive. All right. That is something that I used to remember. So when you deflect the elevator down, camber is increased. So there is a higher lift generation. Okay. So it is positive. Okay. So when you deflect the elevator down, it is positive. Okay. Now let's come back to Cm delta E. For a positive delta E deflection, what kind of pitching moment, like pitch down or pitch up? What do you think is generated? When you deflect the elevator down, is it pitch up or pitch down? Let's just draw this. This is your fuselage reference line. This is your tail. And now I'm deflecting the elevator down. Okay. Deflecting elevator down, delta E positive is down. So what happens? Like I said, camber is increased. So you have a delta L. What do you mean? What is up? I'm not sure what you meant by up. Is it you meant pitch up? Okay. Let's just see this. Okay. Let's just see this. So now when I deflect the elevator down, there is a positive lift generation because there is a camber. Introducing a camber. Effectively, you get a camber when you deflect the elevator down. So there's a positive lift generation. If this is your CG, this change in lift will give you a change in moment, delta M. So that's pitch up or pitch down. Down. Yes. So when I deflect the elevator down, the change in lift is positive. The change in moment is pitch down. Okay, so delta M is pitch down. Pitch down is negative. So which is why this dCm by d delta E is negative. Okay. That you can see, you can verify from your answer. When you deflect the elevator down, there is a negative moment created. Therefore, the derivative dCm by d delta E, that is Cm delta E, is negative. Okay. Okay, let's go to the next question. Static margin during cruise is close to. How do you proceed with this? They've given you the neutral point. Static margin is x bar NP minus x bar CG. Will it be positive or negative? Static margin. Yes, Sandra. X bar NP minus x bar CG. Will it be positive or negative? Yes. For a stable aircraft, it will be positive. So let's just put in the values. They've given you directly. This is 0.56 and 0.32. 0.56 minus 0.32, you get 0.24. Very simple question. Okay. Yeah. Next, for a cruise flight, the delta E required to trim the aircraft is approximately what? What was the formula for delta E required? Or delta E trim, whatever. The delta E required to trim the aircraft. We had that formula, right? So it's just a direct substitution of values into the formula. This is the formula. Okay. Now, can you tell me what will the slope of this graph be? Positive or negative? Slope is nothing but this value. Will it be positive or negative? Just now we saw that Cm delta E is negative, right? Yes. Numerator. So this small thing is negative. Now let's look at the numerator. Is that positive or negative? Numerator is positive. So overall, the slope is negative. Yes, you're right. So slope is negative. As you can see from the answers, they are all, okay, this was, this is the delta E required. Okay, now let's just plug in the values and find out the delta E trim. Cm naught was, what is Cm naught? 0.105. Cm delta E is minus 0.8697. Static margin was 0.24 by minus 0.8697. With CL trim, we had found in the first question. It's 0.763. So let's just plug in these values and find out the answer. They've asked you delta E in degrees. Okay. So remember that your Cm delta E was in per radian. So final angle when you get, it is in radians. Okay. Let's just calculate it. I'm getting minus 0.08985. That is in radians. To convert it to degrees, multiply it by 57.3. Think minus 5.148. Yes, B. That is the right option. Yes. So be very careful about the units asked in the questions and the units that you're using for calculation. Okay. Your Cm delta E we had found in per radians, which is why your delta E came out in radians. Okay. Which is why we had to convert it to degrees. Okay. Next question. Find the elevator control power in per radians. What is elevator control power? How much moment is generated with elevator deflection? Okay, so that is nothing but Cm delta E. Very simple. They've given you 2 points. Yes, dCm by d delta E. Correct. dCm by d delta E. So I just take the 2 points and find the slope. So 0.079 minus 0.025 by minus 0.53 minus 0.07. What is the answer? Minus 0.09. All right. Next question. Lift is perpendicular to free stream velocity. What is parallel to free stream velocity? We have other forces too, right? So lift is perpendicular to free stream velocity. Absolutely right. What is parallel to it? Thrust. All right. So if I keep the engine along. Okay, so let me just see this. If this is your fuselage reference line, and this is RL, okay, and I orient my engines in this direction so that thrust is produced like this. All right. Now, if your velocity is in this direction, V infinity, then the thrust won't be, yes, it's drag. Drag is always parallel to V infinity. Okay, thrust you can't always say. Only in cruise condition, thrust is parallel but opposite to drag. Okay, in other conditions, you can't say that the thrust is parallel to free stream velocity. Drag, yes, is always parallel to free stream velocity. Okay, so these are the two aerodynamic forces. Lift is perpendicular to V infinity and drag is perpendicular, parallel to V infinity. All right. Okay. Yeah, see here, fuselage reference line is given as one of the reference points. So your thrust is, unless you have some thrust vectoring involved there, your thrust is wherever it's fixed. Okay. Okay. Okay, chord line. What angle or what parameter do we measure with respect to chord line? Again, before that, in cruise, your lift is perpendicular to thrust, but not always. Okay, so you can't say thrust. Okay, yeah. So what parameter do we measure with respect to chord line? Where do we use chord line? AC. AC as an aerodynamic center. Aerodynamic center is just the point at which pitching moment doesn't vary with angle of attack, right? Think about something else. Chord line. Something else that we measure with respect to chord line. How do you define angle of attack? Alpha. How is alpha defined? What is alpha? How do you define alpha? Chord line with respect to horizontal. What is horizontal? What do you mean by horizontal? The ground. No, 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 no. Yes, it's free stream velocity. Angle of attack is chord line and V infinity, the angle between these two. So you have the fuselage reference line here, and this is how I mount the wing. So your chord line is something like this, and your free stream velocity is here. This angle is alpha. Okay, you don't measure it with respect to ground or horizontal. No, it is V infinity and chord line. Okay. Stall velocity of the aircraft increases as height increases. True, false, no effect, cannot say. What is stall velocity? What is stall? Just stall. What is stall? Stall. Wings are at heavy load. Can you explain a little more? I did not understand what that means. What is load here? Just elaborate a little. the angle of attack exceeds the max required to generate lift. That is close to the answer. Yes. Yes. Max required to generate lift. For a cambered airfoil, even 0 degree generates lift, right? Max angle of attack. Okay, I think you know it right, but you've not phrased it quite right, but you know what you're saying, correct? Can you just, the previous reply, the wings are at heavy load, I'm not sure I understand what that means. What do you mean by load? And can you just elaborate a little? I'm trying to understand what that means. I'm sure you know what you're saying, but like, I'm not able to understand what you mean by heavy load or load. What is the purpose of wing in an aircraft? What is the purpose of wing in an aircraft? Why do we need wings on an aircraft? Generate lift, correct. So I'm not sure what he meant by load, but okay. So when we take the lift versus angle of attack graph, okay. So this is CL versus alpha. It goes something like this. So it is linear up to a range and then it drops. So this is the point. This is the alpha stall. And this is the maximum CL that the lift, the wing or the airfoil can generate. This is CL max. If your angle of attack goes beyond that point, your lift generated will be reduced. It will not be increasing like you see in the previous case. Why? Why does this happen? So yes, Sandra, your response is, I think you know what you're saying. It just requires a little tweaking in the sentence. The angle of attack exceeds the maximum angle of attack required to generate lift. Yes, more or less, yes. After this angle of attack, it will not generate enough lift to sustain flight, correct. So why does this happen? Till this angle of attack, when I increase angle of attack, lift is being generated, my aircraft is being lifted. After this angle of attack, it's not producing enough lift to sustain flight. Why? Why does this happen? What happens at this alpha stall? Till then, when I'm increasing alpha slightly, your lift is increasing further. I increase it more and I increase it more. Lift increases. After this, if I increase angle of attack, lift is not increasing, it's decreasing. Why? What happens at that point? Just try to think about it. Why is lift generated? Lift. So this is your airfoil. So air is flowing like this. We'll have something else. Okay. This is your free stream velocity. Now there is a pressure profile, something like this, where here it's negative or it's less and here it's positive, right? So which is why you have a center of pressure and there is an upward lift generation. This is how lift is generated, right? This is one of the theories, but this is what, yeah. So now at or beyond alpha stall, what happens? Why is the lift not increasing? Why is it reducing? Just try to think about it from this physics. No pressure difference. Okay, or the pressure difference is in the other direction. Okay, the pressure difference is reversed. Or sufficient pressure difference. Okay, yeah. Why does that happen? Yes, there is no sufficient pressure difference. The bottom surface is not generating enough pressure to push it on top. Okay, but why does this happen? You're right. There is sufficient pressure difference does not exist. Why? What happens? Think about it. So now I think I had shown you this increasing angle of attack, change in pressure profile in the first two classes. So if I increase the angle of attack of the same airfoil, the pressure profile becomes something like this, right? Something, so your that upward curve is shifted ahead. Okay, your CP moves ahead. What will happen if I increase it beyond this? Just try to think. Why is this pressure generated? Because the air is flowing up over the surface, right? On the upper surface, lower surface, air is flowing. So it produces this pressure difference. Correct? That much is clear? Yes. Okay. So now when I increase it beyond alpha stall, why do you think the pressure difference is not there? Just take a minute and try to think. We'll discuss this, we'll come to the answer, but just take a minute and try to come up with the reasoning. The air is flowing on the upper and lower surfaces, which is why you have this pressure difference. When I increase the angle of attack, what happens? Upper wing won't have much flow of air. Correct. So there is a boundary layer separation. Have you heard of this phenomenon? It's called boundary layer separation. When I increase it further, this flow of air separates at a point. So there is no sufficient lift or there's no sufficient pressure difference, like you said. That's absolutely right. Which is why your lift generation drops beyond alpha stall. Okay. So now is stall clear? So a stall is the point at which lift generation is not sufficient. Why does this happen? Due to boundary layer separation. So yes, alpha stall is the maximum angle at which you can operate. CL max is the maximum design lift you can achieve. Okay, I hope this is clear. Now let's go ahead with the question. So they've told you stall velocity of the aircraft increases as height increases. True, false, no effect, cannot say. True. Yes. So our equation was, so lift is half rho v square SCL. In case of stall, you have lift is half rho v stall square SCL max. Now, when I write the equation for v stall, I will have 2L by rho SCL max. When I increase altitude, when I fly at higher altitudes, my density reduces, right? So when density reduces, yes, rho, correct. So when density reduces, your velocity increases. So as the height increases, density reduces and the stall velocity increases. It is true, correct. Okay. Now let's just go over some concepts that we have been going through. I'll just go over it quickly. So static stability is the initial tendency of any object to go back to equilibrium. For an aircraft, in the longitudinal case, it means that it's flying at equilibrium. It suffers some gust, some disturbance. Its tendency to come back to equilibrium or pitch back to equilibrium is static longitudinal stability. Okay. Now, the only condition for a static longitudinal stability is that Cm alpha should be less than 0. This is the only condition. Nothing else affects or nothing else comments about stability. Okay. This condition that we had seen in one of the questions, we discussed this. Cm naught should be positive to trim the aircraft at positive angles of attack. Okay. It's not mandatory. It's not a requirement for static stability. It's just a condition that ensures that you can trim the aircraft at positive angles of attack. Okay. The only condition for static longitudinal stability is that Cm alpha or dCm upon d alpha should be less than 0. Keep that in mind. There will be several questions that say if you deflect the elevator, how much will the stability change? Or if I change the size of the elevator, change the area of the elevator, how will the stability change? It will not. Okay. The factors affecting stability are only Cm alpha. The control surfaces have no effect on that. Okay. Now we'll see, we've seen this, we've derived this, the wing and tail contribution towards Cm. So this is the Cm naught of wing. We just saw this equation. This is the Cm naught of tail. Again, we just used this in the previous question. This is Cm alpha of wing, and this is Cm alpha of tail. Okay, okay. For that, yeah, aerodynamic center is the point about which Cm is independent of angle of attack. What is the aerodynamic center? Is for a wing. For an aircraft, what is it? What is the point about which the Cm is independent of angle of attack for an aircraft? Neutral point, exactly. So neutral point is the CG location at which Cm alpha is 0, but it's the same definition. Yeah, aerodynamic center is for a wing, neutral point is for an aircraft. Correct. So this is the equation for neutral point. Now, if we are to add, so let's see this neutral point. So you take, the way I used to remember this is XACW is there, AC of the wing. And since you're adding other components, if it was just a wing, your neutral point would be AC. Now that you've added a wing, you have the wing contribution towards neutral point. Okay, I mean, you've added a tail, sorry, my bad. If it was just a wing, it will be XAC wing only. Now that I've added a tail, you have the tail contribution towards neutral point. And if you add other surfaces like canard or the fuselage contribution, it will just keep adding here. Okay. Okay. Yeah. Then static margin. Static margin is the difference between the neutral point and the CG. It is just a quantitative measure of stability. So if your static margin is positive, your aircraft is stable. More is it, more the static margin, more the stability. Okay. It is the negative of the slope of Cm versus Cl. Hence, your static margin is positive because your Cm versus Cl for a stable aircraft is negative. Okay. Then we moved on to controls. What do control surfaces do? They enable us to trim the aircrafts at different CLs. Okay, this was your Cm versus Cl. This is where you're trimming, that is your CL trim. Where moment becomes 0, that is your CL trim. Now, if I want to trim at this CL, I deflect the elevator such that your graph is shifted. Right? Graph is shifted. Okay. So it does not change the slope of the graph. It only shifts the graph. So what changes? Slope doesn't change. So what will change? In your Cm equation, Cm is Cm naught plus dCm upon d alpha into alpha. dCm upon d alpha, dCm upon dCl, both are qualitatively same. Okay, so they are both negative for a stable aircraft. So I'm telling you that the slope doesn't change if you deflect the elevator, which is consistent with the previous definition that we had said. Control surfaces do not change stability. So the slope remains same. Okay, what changes then? Upon deflecting elevator, what changes? Slope doesn't change. What else can change? In this equation, what else can change when I change control surfaces? Elevator. Just look at the graph. I've told you that it translates the graph. Okay, it moves the graph. It doesn't rotate it. So when I translate the Cm naught, exactly, Cm naught changes. So this intercept changes. Okay. Another thing to keep in mind is, I think I've discussed this previously, the Cm naught of Cm versus Cl graph and Cm naught of Cm versus alpha graph are different. They are same only for the symmetric case. Okay. Remember this. Okay. So elevator down is positive, that is sign convention. We have just gone over this. The zero lift line changes. What happens that is that CL versus alpha. So initially all tails, mostly all tails for a typical aircraft are symmetric airfoils. Okay. So your CL alpha profile is something like this. Okay. So it goes, your CL naught is 0. So it passes to the origin. Okay. So now when I deflect the elevator down, it increases the camber. So it effectively becomes a cambered airfoil. So what happens? What happens to this graph? This CL versus alpha graph? Does the slope change? When I deflect the elevator down, the camber changes. It becomes cambered. So what happens to the CL versus alpha graph? Which was initially a symmetric airfoil, became a cambered airfoil. Now how will the graph look? What will change in this graph? CL versus alpha. Think about it. Just look at it. What is the difference in the CL versus alpha graph for symmetric and cambered? How will this graph change? This graph. Will it rotate? Will the slope change? Will the intercept change? What is it? Intercept changes, exactly. So it becomes a cambered airfoil. The zero lift line changes. It translates. Again, it doesn't rotate, it translates. Okay. So the intercept from 0 becomes CL naught. CL naught becomes positive. That is the change for a symmetric and cambered airfoil. Right? We had just discussed this. Okay. So yeah, this is what the elevator does. It changes the zero lift line. It changes the camber. It increases the camber. If I deflect the elevator up, it decreases the camber. Okay. Okay. Now, when I decrease the camber, what happens? The line shifts down. Your CL naught becomes negative. Okay. Okay. When I deflect the elevator down, CL or the lift generated is positive. So your CL delta E. For positive, CL delta E is nothing but dCl by d delta E. So for a positive delta E, dCl is positive. For a positive delta E, dCm is negative, which is why this is negative. Okay. Okay. Tau, control surface effectiveness parameter, dou alpha T by dou delta E. Then the equation that we have used multiple times, the elevator required to trim the aircraft at some particular CL. This again has a positive intercept and a negative slope. So it's something like this. This is delta E trim. This is CL trim. Okay. And as your CG moves closer to the neutral point, the slope keeps reducing until it becomes 0 at neutral point. Okay, remember this. Now let's see another question, which is very similar to the one that you had solved in your assignment 2, if I'm not mistaken. Okay, just read the question. For an aircraft, the tail area is 1/4 of the wing area, and distance between the two aerodynamic centers is equal to half of the wingspan, and the wing and tail are in rectangular shape. In addition, the following data is applicable. So they've given you the CL alpha of the wing, CL alpha of the tail, the zero lift angle of attack. That means it's a cambered airfoil. Mean chord, then B span, the CMAC of the wing, tail efficiency factor, CMAC of the tail, XCG minus XAC, wing setting, tail setting angles. Okay. Now let's look at the questions. Very similar to the one that you've done in assignment 2. The pitching moment coefficient at 0 degree angle of attack for wing We just went over these equations. I'll just give you a minute to try and solve this. Go look into your notes and see if you can solve this. Just see the CM naught wing, that is the CM naught contribution of the wing. Okay, we just went over this. We just revised this formula. I'll just give you a minute to try and, understand. If someone could tell me the formula, it will be great. CM naught contribution of the wing. CM naught contribution of the wing. This is the formula. Yes. Can you try and solve this now? Okay, now CM AC of the wing. Here, it's negative. So is it a symmetric airfoil or cambered airfoil? The wing, is it symmetric or cambered? Cambered. Okay. And tail, what about tail? Tail is symmetric or cambered? Symmetric. Okay. Now try and solve this. Then we'll solve it together. In this equation, are all parameters known? CMAC wing, I have told, it's given directly here. CL naught, do you know CL naught? Okay, yeah, continue. Okay. Just let me know if you're done solving. Okay. How will you proceed with calculating CL naught? CL naught is not given to you. How do you find CL naught? Okay, I'll proceed with this. I don't think we can take so much time for one question. How do you proceed calculating CL naught? Just give me an idea. We've done this 2-3 times, in fact, for the previous questions. How do you find CL naught? Just tell me how to start and we'll proceed. Yes. So you have your CL versus alpha graph, and you have CL alpha of the wing, and you have zero lift. So this point is -2 degrees, and you have the slope. So CL naught is CL alpha wing into 2 degrees. So CL naught is 0.09. Both are in per degrees and degrees. So you just have to multiply. So you get 0.18. Plug that in here. So you have your CM naught wing is CMAC wing is minus 0.009 plus 0.18 into XCG minus XAC. This value 0.03. How much is this? Just calculate it. Let me know. So I'm getting, yes, A. Yes, you're right. Minus 0.0036. So CM naught contribution of the wing is negative. That means if there was just the wing, you cannot trim the aircraft at a positive angle of attack. Okay. Next is CM alpha contribution of the wing. And notice that they've told you that it is in per radians. Okay. Can you quickly calculate this? This, I think all the values are given. It's just a quick substitution. Let's just do it together. CL alpha of the wing is 0.09. It's in per degrees. To convert to per radian, what do you do? Multiply by 57.3. Yes. And then XCG minus XAC is given directly at 0.03. So you get, it's divide by pi by 180, okay? So if I just do this, how much do I get? So 0.1546 per radian. That's the value. Okay. So is the wing contributing towards stability, or is it not contributing towards stability? Your CM alpha, the wing contribution is stabilizing or destabilizing? Destabilizing, yes. This is positive. You require CM alpha to be negative for stabilizing. So your wing contribution towards stability is destabilizing. You're absolutely right. Okay. Next, the value of downwash angle epsilon at 5-degree angle of attack will be. What was downwash? What was downwash? What was the cause of downwash? Something. Tell me something about downwash. What was downwash? What was downwash? I think I explained this in all 3 classes. Effect of vortex. Yes. So you have trailing edge vortices at the wing, which travel downward and change the angle of attack and the free stream velocity at the tail. So the free stream velocity seen by the tail is less than the free stream velocity seen at the wing. Okay. Yeah. Similarly, the angle of attack at the tail is not the same as the angle of attack at the wing. Correct. So what is the, how did we find out epsilon naught? Try doing this. Formula was simple. Can you try doing it? These are the formulae. Now, can you do it? I'll give you some like 2-3 minutes. Let's just try doing this. Be careful of the units, okay? You done with epsilon naught? Let's start with epsilon naught. 2 CL naught. How much is CL naught? Yeah, 0.18. Phi E is not given to you. Assume it to be 1. Aspect ratio. How much is the aspect ratio? Okay, let's find out the aspect ratio first. Of the wing. Okay, this is for the wing. Aspect ratio. What is the formula for aspect ratio? What is the formula for aspect ratio? Note that they've told you that it's a rectangular shape. Okay. What is the formula for aspect ratio? General formula. Forget about rectangular wing. B square by S. Exactly. So it's B square by S. Since it's a rectangular wing, it is B by S is B into C. So you just have B by C. B is 26 and C is 2.2. Okay. So plug that in here. Aspect ratio is 26 by 2.2. How much is epsilon naught? Is the value? I don't have a calculator. Just tell me the value. I'm getting something like 0.0096. Is this right? Just calculate and let me know. I'm using the calculator on my phone. Yes. Okay. So what is the unit of this? What is the unit of this? Yes, 0.0097. Okay. What is the unit? What is the unit? Epsilon is an angle. So it is, yeah, this formula is valid only for radians. So this is actually in radians. We need to convert it to degrees because your answer they've asked you in degrees. Okay. So it says degrees. We need to convert it into degrees. Okay. What do? Multiply by 57.3 and you get something like 0.555 degrees. Okay. Okay. Now let's find out the slope. Just plug in the values here. Keeping in mind that this formula gives you value only in radian and this formula needs input value should be in radian. This output is radian, this input is radian. Okay. This slope has no unit because epsilon and alpha both are degrees, both are angles. Okay. So what is the value of the slope? D epsilon by D alpha. 2 into CL alpha wing. What is the value of CL alpha wing? Should we use 0.09 directly? No, correct. Absolutely right. 0.09 into 57.3 divided by pi is not given as geometry 1. Aspect ratio was 26 by 2.2. What is this value? This has no unit. Okay, it's this ratio of two angles. Slope is something around 0.2778. Correct? Let me know if I'm going wrong somewhere. Yes. Okay. Now they've asked you what is the final epsilon. They see the options have 0.555. This is to confuse you. All right. They've asked you the complete downwash angle. So the complete downwash angle is epsilon naught plus d epsilon by d. Let me write that neatly. All right. D epsilon by d alpha into alpha. Okay. Now plug in all the values and tell me what is the complete epsilon. Epsilon naught is 0.555 plus 2778 into 5. What is the value? What is the value? See, they have been very tricky with the options. They've given you 0.555 directly. It's just to, yes, it is 1.194. 1.94. Okay, so the option is wrong. 1.94. Okay. 1.94. Okay. Right, so be very careful. They've asked you the value of the downwash angle, not just epsilon naught. Okay, the entire thing. So you are using this linear approximation to find this epsilon. Epsilon naught plus dou epsilon by dou alpha into alpha. Keep in mind what are the units, what you should use here. This equation gives you in radians. Okay. And this equation takes the input in per radians or radians. Okay. Remember this. Okay. The pitching moment coefficient at 0 degree angle of attack for tail, Cm naught tail. How do you proceed with this? Could you explain the units again? Okay. Let me just. Okay. So these are your two equations. Here, this value gives you output. Output is radians. Okay. This formula, the input is per radian. Okay. Everything is in terms of radians. And this one's output is unitless. Because it's a ratio of two angles. Okay. Remember this. I'll just, okay. You remember this, right? So output is in radians. In this case, input is in per radians and output is unitless. Okay. Yeah. Pitching moment coefficient at 0 degree angle of attack for tail. tail contribution towards Cm naught, tail. What is the formula? I'll give you a moment to recall it. Initially, we did Cm naught contribution of the wing. Now it is Cm naught contribution of the tail. What is it? Okay. So this is a formula. Can you try and do it now? I'll give you a few minutes to try and solve it. In this equation, you know the efficiency factor, you know CL alpha tail, you know I wing, it's given in the question. We found out epsilon naught, I tail is given in the question. What is unknown is VH. How do you find out VH? What is the equation for VH? Formula ST upon S, LT upon C, C bar. Okay. Yes. Just think about this for a moment, read the question carefully again, and then we'll try to solve this. What is ST? Can you at least tell me what it like? What is the term? What does it represent? ST is what? What is ST? Tail area. Okay. So ST upon S. S is the wing area. ST upon S. Can you find out? Just read the first line of the question. For an aircraft, the tail area is 1/4 of the wing area. So ST upon S is 1/4. Okay. Now what is LT? C bar is given to you. What is LT? LT is XAC of the tail minus XCG by C bar. C bar is given to you. I'll just put in that value. C bar is 2.2. How do you find out this numerator? XAC tail minus XCG. Read the question carefully and tell me how to find it. So in the question, it says distance between the two aerodynamic centers is equal to half of the wingspan. Correct? So what that means is XAC tail minus XAC wing is B by 2. And B is what? 26 by 2. So this is 13. Correct? What we need is XACT minus XCG. Yes, Sandra. We'll start with the correct. You're right. Start with that distance between two ACs. So this is what is given to us. What we need is XAC tail minus XCG. Another thing that they've given us is X bar CG minus X bar AC. Right? So this is given is 0.3, 0.03. So XCG minus XAC is 0.03 C bar, which is 0.03 into 2.2. How much is that? How much is that? So you have 0.066. Now, this is XAC wing. So this is equation number 1. This is equation number 2. If I subtract these two equations, I will get XAC tail minus XCG. Right? So if I do this, then I'll have 1 minus 2. So you will have XAC tail minus XAC wing. How much is this? Sorry, XAC tail minus XCG. How much is this value? It's just 13 minus 0.066, which is 12.934. So this value you plug in here and you get VH. So VH is equal to 12.934 divided by 4 into 2.2, which is, how much is VH? $1.469. Correct. Now you use it here. So you have 1.469. Eta is 0.89. CL alpha of tail is already in per degrees, 0.059 into I wing is 1.3. Epsilon naught was 0.555. Tail setting angle 1.3. So what is the final answer? The options I'm giving here. So I'm getting something around 0.243. This is the CM naught contribution of the tail. Yes, 0.243. Okay. You understood this? So in this case, it's not much of a difference from 13. So you can actually directly use this 13 because it's just 13 and 12.934. Difference is only 0.066. You can directly use 13. Okay, difference between the two ACs in this case, not always. Okay. Next, the pitch stability derivative of the tail. So tail contribution towards CM alpha. What was the formula? This was the formula. VH we just calculated. All the other parameters you know. Try doing this. And this is not here. It's just this. Just calculate this and tell me. All the quantities you know, it's just a direct calculation. I'll just give you a couple of minutes to do this. And see, you can do it quickly. let me try putting in the values. So VH was 1.469. Eta is 0.89. CL alpha tail 0.059. This is in per degrees, your d epsilon by d alpha. And they've asked you the final value in per radius. We'll do it at the end. Okay, this is in per degrees. So 1 minus d epsilon by d alpha was how much? 0.2778. How much is this value? Let me just calculate it. So I'm getting minus 0.0557 per degrees. Per degree. So I multiply it by 57.3 and I get minus 3.19. Yeah. Did you get D? I'm getting minus 3.19. Sandra, can you just check your calculations again? It's in per radians, okay? I think your answer is yes. Yes. Yes, you must never forget the sign. That is very important here. Look at the options. They have all the signs. I mean, they have a combination of the signs. So now that your answer is minus 3.19, or the closest one is here. So is the tail stabilizing or destabilizing? Stabilizing, yes. So your CM alpha contribution of the tail is negative, like we desire it to be. Hence it is stabilizing, correct. Now, if the fuselage contribution towards CM alpha is equal to 0.99 per radian, so your CM alpha fuselage is 0.99 per radian. The difference between neutral point and aerodynamic center of the aircraft in meter will be, it should be aerodynamic center of the wing. Not aircraft, it should be wing. Because aerodynamic center of the aircraft is neutral point, okay? So difference between the aerodynamic center, neutral point and aerodynamic center of the wing will be, they've asked you, x neutral point minus x AC wing. This is the question. Any ideas? Just read the question properly and think about it. I'll give you some time to think about how you will come up with this. I'll just show you the neutral point equation once. So this was your neutral point equation, right? XNP is XACW. So they've asked you this. XNP minus XAC wing. That is what they've asked you. Okay. Let's just go back here. Yeah. Read the question and think about how you will solve this. Note that they've given you the CM alpha contribution of the fuselage also. So here the fuselage is stabilizing or destabilizing? Destabilizing, correct. Okay, now let's think about how you will proceed with this question. Let me show you. So this is the formula. What we had studied till now was just this part. This is the wing contribution. This is the tail contribution. Now that you have a fuselage, it is this new quantity is added. How? Let me just tell you. So whatever new components are added, you go on adding like this. So you have x bar NP. What is the wing equivalent of that is x bar AC. What is the tail equivalent? You subtract it. Okay. So you keep subtracting these components from XNP. So basically what it's doing is it's moving your neutral point backwards. If there was just wing, if this was your neutral point, if this was your fuselage reference line and you had just your wing, neutral point and AC wing would be the same. Okay. Now I've added a tail. So I added one AC tail. So it is pulling your neutral point backwards. So this is the first case. In the next case, your neutral point would be here. Now I'm telling you that the fuselage is also contributing towards it. So it is pulling it backwards. So neutral point 3 would be further backward. Now if I add a canard, if I add AC canard, it's pulling it forward. So your next neutral point would be somewhere here. You understand? So as and when I go on adding these components, the neutral point is pulled backward and forward towards these components. If it is just the wing, it is just AC. When I add a tail, it is pulled backward. When I add a canard, it's pulled forward. Okay. So you go on subtracting these components. So if it was a canard, then I will add it. If it is all the other components, then I will subtract it. So XAC wing minus, it is CL alpha of the tail by CL alpha of the wing. Now the CL alpha of the tail, you cannot use it as such. It has other components associated with it. Okay. So it has VH and all of those things. Then you have CL alpha fuselage minus CL alpha wing. So this is, let's put a star, and so this is the starred one. Now if I had a canard, I will do CL alpha canard by CL alpha wing. Okay. And the CL alpha canard again will be starred. It will have all of these components, canard, volume ratio, and all of those. Okay. So in this case, it's the first three components. Can you just plug in the values and tell me what XNP, X bar NP minus X bar AC wing would be? This quantity and this quantity. Just plug in the values and tell me. Take a question, so I'll just erase and write it again. So your X bar NP is X bar, I'll just do minus X bar AC wing is minus of minus VH. VH was 1.469. Okay, this quantity we have calculated. This is CM. Okay, my bad. It is CM. The formula is wrong. Sorry. I'll just write this again. Okay, 1 minute. Okay, so this is supposed to be CM. So your X bar NP is X bar AC wing minus CM alpha tail by CL alpha wing and minus CM alpha fuselage by CL alpha wing, so on and so forth for each component. Okay, so just do it now. This is CM. I made a mistake in the equation. It is CM alpha fuselage, which is given in the question. Let's do it. X bar NP minus X bar is C wing, this is wing, is minus of minus, what is it? 1.469. Eta is 0.89. The CL alpha of the tail to 778. Correct? Yes. Minus 0.99 by CL alpha of the wing. CL alpha of wing is 0.09, but your 0.99 is in per radians. Okay, so the conversion you need to be very careful. So here I will just do 57.3 because CL alpha wing is in per radian and this is in per degree and this is in per radian, which is why I've taken this 57.3 in the denominator. But for CL alpha of tail and wing, they are both in per degree, so there is no conversion there. Okay, what is this value? Just a minute, give me a minute. Meanwhile, you continue calculating it. Yes. Can you tell me the value? So just realize that we have just calculated this. So this quantity we have just calculated as CM alpha of the tail. Okay. So you have, I'm getting it something around 0.4271. Are you getting this? Okay, I'm getting this value. Just let me know if you're getting a different value. And this is X bar NP minus X bar AC. So multiply it. So X NP minus X AC wing is 0.4271 into C bar. How much is this value? C bar is 2.2. So I'm getting 0.9 something 94 plus 0.94. Yes, 939. Okay. Okay. So is the aircraft stable or unstable? You can't conclude from just X bar NP minus X AC, but from the other quantities that we've calculated, your CM alpha is negative. So the aircraft is stable. Okay. Let me just see this. See, CM alpha of the tail is minus 3.19 and CM alpha of the wing was positive 0.156. So overall CM, the overall CM is CM alpha wing plus CM alpha tail, which is negative. So the aircraft is stable. Okay. Okay. Now let's go to the next question. Yeah. The pitching moment coefficient CM versus angle of attack for a large jet transport can be seen in the figure below. Use the table along with the two equations. That is CL is 0.03 plus 0.08 alpha. CM is 0.03 minus 0.02 alpha. where CL is the lift coefficient of the complete airplane and alpha is in degrees. They've also given you CG location. So is the airfoil, or if this was just a wing, is the airfoil symmetric or cambered? Looking at whatever data is given to you. If it was just an airfoil or a wing, yes, cambered. Cambered, why? Because your CL naught is positive, CM naught is also positive. Actually, CM naught positive is only for an aircraft. So just see this. If it was just this, it's a cambered airfoil. If CM naught is positive, the airfoil is reflex. Right? Yeah, okay. If this was an airfoil, this is the answer. But it's for the entire aircraft. So let's proceed with the questions. Yeah. The elevator control power in per degree will be. We just did a similar question. How do we do this? Very similar question we just did. How do we do this? What is elevator control power? What is the term? Yes. Cm delta E, which is dCm by d delta E. So just take those 2 points and find the slope. Very simple. So it's 0.031 minus 0.016 by minus 8.5 minus 1.3. What is the value? Everything is in degrees. They've asked you in per degree, so no conversion required. D is minus 0.0015. Next question. Find the stick fixed neutral point. What is, I don't think Sir has completely done this, but what, in your opinion, is stick fixed and stick free? What is the difference? What do you think? Sir has mentioned this in his class multiple times, in fact. Yeah. What is stick fixed and what is stick free? What is the difference? I think in the next couple of lectures or the next week, we will be discussing stick free neutral point. But what do you think? What do you think it means, stick free and stick fixed? Okay, so in an aircraft, you pull a stick to deflect your elevator. And if you hold the elevator, if you want to hold the elevator at that point, you have to hold on to the stick. So you're assuming it to be fixed. You're assuming the elevator to be fixed at the deflection that you want. But ideally, this is not the case. You will let go of the stick and the elevator is allowed to float freely. That is the difference between stick fixed and stick free. He will get to stick free in the next week, I think. But this is the idea behind it. Okay. So now how do you find this neutral point? Given the data, how do you find neutral point? Static margin. Exactly. Very nice. So static margin is minus dCm by dCl, which is x bar NP minus x bar Cg. So minus dCm by dCl. So I will just modify this and write it as minus dCm by d alpha into 1 by dCl by d alpha. This is all right? Yes. So you have minus dCm by d alpha is plus 0.02 and dCl by d alpha is 0.08, which is, what is this value? 0.25. So x bar NP minus x bar CG is 0.25. and x bar NP is 0.25 plus XCG, which is again 0.5, it's 0.5. Okay, it's 0.5. Okay. Now, oh yeah, this is the formula that we used. Okay. Next question is the zero angle elevator trim, delta E naught in degrees. How do you find this? Again, you know the equation. So this is from delta E trim is delta E naught plus d delta E by dCl into CL trim. This is the slope and this is the intercept. This is what we have to find out. Can you just substitute the values and tell me what is delta E? Delta E naught. We have all the terms, just substitute and tell me. What is CM naught? Zero 0.03, yes. What is CM delta E? We calculated it. Delta E is minus 0.0015. How much is this value? 20 degrees. Plus 20. That means the elevator is deflected up or down. Plus 20. Up. Correct. Absolutely right. So this is upward deflection. This is upward deflection. All right. Now next question. The aft center of gravity limit, XCG by C. Aft means as far as you can go. What would this value be? XCG, current XCG is given, but how far can you move the CG? Think about it. This is the last question we'll be dealing with today. Just think about it. So what is, in terms of CG, what is the condition for stability? You remember that simple word that I told you, CAN for stability? Your CG should be, if it is just wing, CG should be ahead of AC. If it is an aircraft, CG should be ahead of neutral point. This is the condition for stability? Yes. So how far can you move your CG? How far behind? Aft. Neutral point. Exactly. So the aft center of gravity limit for an aircraft is the neutral point. This is X bar NP. So the answer is, how much was our X bar NP? 0.5. So that is the answer, 0.5. Okay. So the maximum limit at till which you can move your CG is the neutral point. After that, your aircraft will not be stable. Okay. So I had another set of questions to discuss, set of questions given some data. So I don't think we'll have time for that. I'll use that in the next class. So I hope you all learned something. I hope it was understandable. Is there anything, any doubt you have, any question from what we discussed so far? Today's or previous lecture or anything? Also, there was one question put up on the forum. Let me just get to it. What was the question? Just a minute, let it load. Meanwhile, you can tell me if you have any other questions. Yeah, the question on the forum was basically the gist of it was CL neutral point varies as CL varies. Is that correct? The question was, as CL varies, neutral point changes. Is that true? Does neutral point change with CL? What was our definition of neutral point? Neutral point is the CG location at which CM alpha is 0. Look at the equation for neutral point. Look at it and tell me if it varies with CL. Your CL is CL naught plus CL alpha into alpha, which changes throughout the flight duration with change in alpha, right? CL keeps changing throughout the flight because alpha keeps changing. So throughout the flight, does the neutral point keep changing? No, right? So that was our definition. That was our reason for picking aerodynamic center or neutral point, to pick a point that doesn't change throughout the duration of flight. That point that is independent of angle of attack. Since it's independent of angle of attack, it's also independent of CL. It depends on CL alpha T, CL alpha wing and all of that. But those are fixed parameters. None of these parameters are changing, right? Maybe the downwash up to a certain extent will change, but it's more or less the d epsilon by d alpha will be same. Okay, so neutral point is fixed for the duration of the flight. It only changes with its aerodynamic derivatives, which is fixed for an aircraft. It doesn't change during the flight. Okay, neutral point does not change with lift or angle of attack. That is by definition. That is how you came up with neutral point. Okay. Okay. So I think with that, we'll complete this tutorial session. If you have no other questions, then we can end it here. After this lecture, I think by tomorrow, I'll post this on YouTube. But till this lecture, it is posted on YouTube. The slides I'll be posting immediately. So if there are no other questions, then we can end it here. Thank you very much. Good luck for your assignment, and we'll meet again next Tuesday. How to find this video? It's on the same. Okay, I'll just post the link of the previous video. It's on the same playlist. Okay, just a minute. So this is the link of the previous video. You can find the other videos on this channel. It's in the same playlist. Okay. It's also posted on the NPTEL problem discussion session. You can check it out there, or you can go here. I'll be posting this video maybe by tomorrow. Okay, if there are no other queries, we'll end it here. Thank you. We'll meet again next Tuesday.